semester 2026 for our course Emerging Technologies for the Circular Economy. Sorry. Yeah, after some introductory lessons or an introductory session, the short circular economy session, and then Anand's extensive LCA sessions, we are now coming to another main part of this lecture series, which is going to be the Internet of Things that we're going to spend quite a lot of time with. So today, it's the introduction to the Internet of Things, like what is this at all? Do we have some examples to get a better feeling about this? And then in the subsequent parts of today, but also in the next few weeks, we'll then look into the different building blocks of the Internet of Things. So what are core components? What are different varieties of those components? What do I have to consider when building my own IoT applications systems so that they're really serving the purpose that you have in mind? And all the talk about the circular economy, sustainability, but also Anand's LCA sessions in the last 2 weeks are supposed to prepare you or to help you putting different existing IoT applications, but also when you're designing some of them yourself, to better judge, do they really have a positive impact in terms of sustainability, or is it just like pretending to help us to move forward to a more sustainable future? So essentially, is it greenwashing or not? The answer is often not quite clear because it's not always just about sustainability. We'll have a few examples in the next slides as well. But at least it should help to prepare your mind to be a little bit more critical with respect to proposed greenwashing solutions. Without further ado, let's get started. So, as always, our slides and videos are all uploaded and freely available. You can grab them whenever you like. Let's start with some news and updates or more reminders. For the mining students, you have the upcoming IoT coding workshop on the 23rd and 24th of July. We'll communicate further information ahead of time. Just note that it's going to be at Digit in Goslar. We'll communicate further information with respect to what do you need to bring, when exactly do we start, when do we end, and so on and so forth, like 2 weeks or 2.5 weeks before the actual coding workshop. We also finalized the exam dates by registering them with the examination office. So for the mining students, it's going to be an oral exam on the 12th and 13th of August, while the ETCE students, because there are just so many more, have to do a written exam. It's going to be online. So you don't have to get somewhere except for making sure, or except for a place where you have a stable internet connection. But once again, we'll also communicate more detailed information ahead of time. This is just something for you to keep in your calendar so that you know when we're going to test your knowledge. That's all about news and updates. We'll probably put the evaluation questionnaire in the next lesson or the next lecture, because I just received this email earlier today and we did not manage to integrate it here. So we'll have a news and update section next week again. And that brings us to the recap part. So at the end of the circular economy session, we also thought a little bit about the nature of technology. We briefly touched upon the thoughts of a guy called Brian Arthur, who stipulated that an economy is an expression of its technology. And we essentially wrapped up that lecture by combining this thought with a circular economy, and that there is a case to be made that the current unsatisfying state of the circular economy, because we want to go there, but we don't have it yet, might be a reflection of a lack of sufficiently developed technology to make actually this circular economy work. And all the stuff, the IoT that we're now going to talk about in the next lectures until the end of this course, are essentially one attempt to create another building block that finally makes a circular economy more tangible, or happening at least in part. Of course, it's not just the Internet of Things and a little bit of machine learning and AI that is missing to make the circular economy work. There are also, of course, other building blocks, But we, as computer scientists and some mining students who would like to learn more about computer science, we're going to look into this direction. And I'd also give you the life cycle assessment background to properly assess whether a certain IoT application is suitable to make us move towards the circular economy, or it's just greenwashing. I already said that in introduction, but those essentially more serving as a recap reminder. We also looked at this figure before, and we're gonna have it in our slides again and again and again. I'm gonna skip a little bit over it now because in the later parts of this lecture, we're gonna build this slide bottom up and top down so that you have a little bit more better understanding here. So let's start with a little introduction and history of the Internet of Things. It's become quite popular now. Essentially, everything is somehow smart. Smart homes, smart watches, smart glasses, smart cars, and so on and so forth. But the origins of this idea go back even further, and like many, many decades. Even those initial thoughts are even actually older than I am. The first things that you could consider to belong to the Internet of Things go back to 1982, where they had a beverage dispenser with an internet connection, and that, in a very broad and very simple, rudimentary way, already could be considered the first idea of the Internet of Things. So you had a thing that was connected to the internet. It's very basic, it's very fundamental, it's not super fancy, but it fits somehow some of the definitions that we're going to look at later. Over the next decade, up to 1991, then this idea or this vision of the ubiquitous computing developed. Essentially, the idea being I have differently sized, shaped, formed, capable devices that are relatively ubiquitous in my environment, in my daily life, and they have the computing power. This nowadays seems to be totally weird because everyone has a smartphone, everything has certain computational capabilities. Even the USB stick that I can use to skip slides back and forth has some kind of smartness in it. More or less everything is smart nowadays, but this idea that this actually becomes true at some point in the future was not really something that a lot of people imagined back in 1991, where this vision of this ubiquitous computing came along. In 1999, a guy called Kevin Ashton referred or used the term IoT when he referred to the linking of clearly identifiable physical objects or things with a virtual representation in an internet-like structure. So it's not just about having a thing in reality and just plugging internet in or giving it Wi-Fi access. It's also having this duality of an object in the real world connected to the virtual representation of that same object in the internet. And both of them working in sync and essentially keeping themselves in sync so that the real beverage dispenser is not running out of, I don't know, Coke or whatever, while the virtual representation of the same thing says, nope, it's still fully stocked and no one has ever bought a Coke or a soda in the last 4 weeks or so. So this virtual representation should always represent the real world and vice versa. And the Internet of Things has like many facets. There are various examples that you probably are already using in your day-to-day life, like smartphones. Everything essentially is Wi-Fi connected, but we'll also look into further connection protocols there. It's a smart washing machine, your smart key, your AirTag to find your keys, your notebook, your tablet, your smartphone, the smart light bulbs in your home, whatever. So essentially everyday consumables and consumer products that have some kind of connectivity and smartness already built in. But there are also applications, for example, in the agricultural sector, being it just systems that automatically water large areas according to a schedule or based on need. So if it just rained, I do not need to water and irrigate my fields, but the soil humidity or the soil moisture reaches a critical threshold, that might automatically trigger some kind of irrigation system. But it can also be something like drones to monitor the growth of certain plants. It can be automated harvest systems that harvest fields on their own. So there are a lot of different applications just within this small subfield that all belong to the Internet of Things. You can also think about energy consumption here. So if you think about a solar panel or a larger solar installation on a house, you might want to use as much of this electricity while it's available, so throughout the day. So this is where you maybe want to have your clothes being washed, where you want to charge your battery electric vehicle so that it goes straight from the roof where you have the solar panels into the car. If you have an excess of energy, you might want to put it in some kind of storage, a battery storage. Maybe your car is able to store an overhead of energy that was collected during the day and then put it back into the system at night to then feed something like your freezer and so on and so forth. All of that also just another application of the Internet of Things where you're sensing information and then using them to make certain decisions. Security and surveillance, just another example, smart cameras or just dumb cameras that are collecting video feeds, audio feeds, which you then can use to track certain behavior or people and then make decisions. Telemedicine, smart homes, we'll get to some more examples in the subsequent slides, so I'm not going to go and close that circle because the next few slides are essentially just about giving you examples and then also having some specific examples for you to later look up. So let's go to one example that is quite popular in Lower Saxony as the place where one of the largest auto manufacturers worldwide exists, Volkswagen. So this idea of not just having millions of cars on the road, but making those cars also communicate either with headquarters or among each other is already quite old. So things like the dartboard challenge go quite a while back, even though there the focus was mostly about the cars being able to drive and navigate themselves, and not too much talking about to each other about that. But those things are also somehow related. So if you want to have a car that can drive itself and navigate itself, you need to learn about the environment. So where am I? GPS navigation or GPS positioning, for example, or having a very high detailed map in storage in your battery system so that you understand, okay, this is where I am. Then understanding, is there someone in front of me? What is this other someone or something in front of me doing? Is it accelerating? Is it braking? Is it steering left? Is it steering right? Those kinds of things are sensing, and then you have to make sense of that data. The sensing becomes much easier, or it becomes somehow easier, if you're also then not just doing all of this yourself, but if you're able to communicate with other things around you. So if the car in front of you just tells you, look, the navigation system says I'm going left in 200 meters, then you can already prepare for that as an autonomous car that is also supposed to drive itself. If you can then access internet information like where are traffic jams, what is the weather report, is there a construction site that will slow down traffic, all of those information are other ways to sense and learn about information pertaining to your environment. So all of those things also coming together here. So it's on one hand computation and sensing inside the vehicle, but also getting information somewhere from the cloud where further information can be provided and or obtained by a vehicle. We're not going too much into detail about how this now works on a technical level, because this is not the course for this. It's more to give you an idea, okay, this is also considered to be part of the Internet of Things. Another example that follows this idea of autonomous cars, but abstracts a little bit from this, is the idea of the so-called machine to everything economy. So let's suppose we have not just smart autonomous vehicles that can drive itself, but a even more smarter and more advanced technological environment. So not just machines, it's not just cars that are super smart and can do stuff on their own, but it's also more and more machines, up to that point where machines, for example, can become independent business actors and then provide services to you. So this idea of transportation as a service, where a car earns, or an autonomous car that can fully autonomously work, offers you transportation services that you then pay for. It would be, for example, one idea of this machine to everything economy. And it requires not only this idea of, okay, autonomous driving, but also the ability to communicate with people who are looking to be transported. But it also doesn't only have to be humans, it can also be parcels, for example, that those need to get from A to B. We once had a research project at our institute that was called Hitchhike Box. The idea was pretty simple. You would essentially give a parcel $5, and then it has to somehow hitchhike to its final destination while only having those $5. Also, transportation as a service, trying to get as close to your final destination as possible with the constraint of having money there. Another example that falls into this machine to everything economy is the so-called machine to machine interactions or applications. So we had discussed in the previous slides that machines like cars might communicate with each other to better predict and sense and understand their environment. But there can also be a business aspect involved here. So let's say you have a car that needs to urgently transport someone to the airport, and another car who's not on a tight schedule. So if there is a traffic jam, you could think about examples or scenarios where you might pay someone to let you slip through so that you can get faster to your destination. It essentially is built on this idea of, in a traffic jam, the space on roads is a scarce resource. Otherwise, there would be no traffic jam. If there would be more road than necessary, then you don't have traffic jams. If this road is blocked, road space becomes a scarce resource, and then you can start essentially trading it. It's obviously a little bit of a far-fetched scenario, but simple implementation like priority lanes or toll roads are essentially very simple versions of the same idea. You pay something and then you get to ride on the or drive on the nice roads or the faster roads or whatever. Pretty much simple concept, just that here those intelligent machines would do all of that themselves. A final example from the space of the machine to everything economy is the so-called machine to infrastructure applications. So you have this autonomous car, it offers transportation as a services to make some money. And you also have cars talking to each other and even maybe negotiating some road space with each other. And now machine to infrastructure is essentially the idea that they also can communicate, but also interact or enact business endeavors with infrastructure components. So that could be something like smart parking, that I can just leave the car, or that the smart car can just park itself and automatically pay. But it can also be something like battery charging, that you just drive by, the car is automatically charged, or that you get real world traffic information that are super recent and super detailed and super reliable. All of those things would also then fall in this machine to infrastructure component. But this, once again, just being like a very small field here, even though that in itself it's quite big. We're skimming a little bit through the examples just to give you an idea of the range of Internet of Things applications. Yeah, and this is essentially just a short wrap up to better understand how machine to human, machine to machine, and machine to infrastructure and machine to everything are related. Essentially, the first three together then constitute this machine to everything economy. There are some, admittedly now slightly older videos where some of our research was then involved in making some proof of concepts or prototype for this kind of stuff happening. It's a now defunct startup, but you can watch the videos for entertainment purposes. I just checked the links, they should still be online. Good. Now coming back to the farm, the agricultural applications of the Internet of Things. So we talked about irrigation already, or automated harvesting, so fleets of drones or some kind of robots or tractors going there. But you can, of course, also get even more information from the farms itself, being it now animal farms or being it just plant farms. It's not just about, okay, how wet is the soil, when did it rain the last time, but also the temperature, the wind speed, the amount of sun that you're getting. Are there any missing nutritions in the soil? Is there some kind of a pest ravaging through your systems? So all of those information, or all of those are data points that you then need to process to make any decisions about what you should do on your farm. Should I water today? Should I not? Should I fertilize? Should I not? Same is then true for animals. What I can learn about the environment of plants, I can also apply to animals. So still water for the cows or the chickens or the pigs. Is the temperature in their dormitory correct? Do I need to start a ventilation system? Do they still have some food? Can I learn something about their well-being? Are there any diseases, and so on and so forth, which then should trigger certain actions that need to be handled or that need to be enacted. So similar to the car example, it's first sensing, getting data, learning about your environment, then using this to design, to synthesize knowledge, and then do something about it. Healthcare promised that we get here as well, and this is now one of the things where it's already like a good example that this idea of judging or critically assessing IoT applications just in terms of sustainability is obviously too narrow-minded. Because is it more or less sustainable if we prevent heart attacks, or if we make it, or if we design IoT applications that notice, okay, your heart is making weird things, it's going too fast, too slow, or it's skipping a beat. We should automatically notify a doctor to get to you in time before you die. Is it more or less sustainable? That's not really the metric that you're measuring here. So we're also going to look, of course, at applications of the Internet of Things that are not just purely sustainable or unsustainable. There are also categories here, even though we are mostly focusing on how can we develop technologies that foster a circular economy. This would go a little bit more in the circular society direction, not so much in the circular economy direction. So you can have a smartwatch that detects whether your blood pressure isn't working fine or if your heart is doing weird things. For elderly people, you can also think about motion sensors. So did someone drop and fall down and cannot get up anymore? You can detect something like that with motion sensors. If you have diabetes, blood glucose might be an interesting thing. Temperature sensors also to figure out, is someone too cold, too warm? Did they have enough water intake, and so on and so forth. So there are like different things where there are different applications where you can design systems to automatically sense certain information about the environment, then once again use this information to derive and synthesize knowledge, and then make decisions based on that. So using this kind of information that you collect, gathering them, processing them, and acting them, like calling the ambulance because someone just has a heart attack and there might be a chance to save that person. There are also applications in the retail sector, so the smart retail part, not my favorite field of application, but we should at least mention it. So there are shelf sensors that alert staff, hey, we're out of pasta, please put your pasta in there. If that's really necessary is up for debate. The part that I don't like that much is essentially then this engagement improvement thing. So, hey, you came here to buy pasta and only pasta, but can I also interest you in a deal of chocolate? Because in the past year, you bought chocolate 500 times. I know you didn't come here to buy chocolate today, but what if I give you 5% off to make you buy something that you didn't even need or that you didn't even want when you came here? So those kind of things are also very much part of this. Mobile self-checkouts can be quite nice if you don't like to stand in a line, but maybe you're just standing in a self-checkout line then. Virtual fitting rooms are actually something that you could consider helpful. So making sure that whatever you want to wear then really fits your body and you already know what it looks like. So there are also applications there with a certain that can be helpful or not helpful, and that can help to have at least some minor impact on sustainability or are just unsustainable or fostering unsustainable behavior. There's also a category that falls in the direction of disaster control, disaster prevention, or disaster handling. So here's an example for a tsunami warning system. But the same might be true for hurricane warning systems, flash flood warning systems, snowstorms, or whatever. Essentially, the idea always being the same. You place sensors in locations where you expect certain things to happen, and where you then try to measure indicators that give you information about the direction of a hurricane, or whether an earthquake appears, which might trigger a tsunami, or if there was rain upstream somewhere in the mountains, and then afterwards the river bed or the river level rises, you might have to evacuate people because there might be some kind of a flash flood. So it's more or less always the same. You place sensors, you monitor how the values that the sensors provide change given certain external events that you already anticipated, and then you have to do something in case certain thresholds are crossed. So in this tsunami early warning system, the idea was quite simple. I'm not sure if you're old enough to, for example, remember those tsunamis that hit Japan and then caused the Fukushima nuclear reactor to get in trouble, or even before that in, I think it was Thailand, where they had this huge tsunami that killed, I think it was actually hundreds of thousands of people, or quite a lot of people, because they could not be brought to safety early enough. So the idea essentially being you place sensors that only notice, okay, there was an earthquake, because earthquake happen way more often in certain areas than you might think, but not every earthquake causes a tsunami. So you monitor for earthquakes, and then you put additional sensors there to monitor, is there some certain behavior in the water that then indicates, okay, we have X minutes based on simulations or past experiences to evacuate those areas, hoping to avoid certain death scenarios that might be quite undesirable. Smart grids are essentially the extension of this example that I gave earlier with the solar panel on your roof, and then trying to maximize the use of the electricity that you're generating by either running your washing machine on time or charging your battery electric vehicle. But it also, of course, extends to the whole grid as a thing. So in Germany, we're now having quite a lot of solar energy capacity. We also have quite a lot of wind farms, but both of them are weather dependent. So the sun is usually shining during the day and not at night. Wind farms produce energy when there is quite some wind, and you cannot really control when both of those happen. So maybe there's a bad weather and you don't have any solar. Just bad weather also doesn't give you a guarantee that the wind farms are producing properly. So you have to somehow still, at least for now, if you don't have like enough battery storage, to buffer for those bad times, you still need something like thermal power plant or nuclear power plant. And you want to keep them at a minimum because you want to use the renewable energies, but you still need them, and you need to also coordinate them. So as soon as you notice, okay, the solar farms are dropping now, you have to get more energy either from the wind farms or from the thermal/nuclear power plants. And all of this somehow has to be coordinated because the grid system is rather sensitive when it comes to changes in power supply and power consumption. You always have to somehow keep it in a stable level, and that requires also some kind of smartness. So once again, you're measuring something, deriving knowledge from those measurement points, and then doing certain actions that give you a desired outcome. There are also smaller use cases that can also be very regional or even local. You can think of positioning services or so-called location as a service applications. So most of you are familiar with GPS or Galileo, or I forgot what the Russian version is named. Jonas, something like that. That work very well outside. So you get somehow precise location information about where you are up to a certain few centimeters to meters. But main limitation is that they do not do very well indoors because you might not have a good enough reception in there. Or if you are in a very dense city with high-rise buildings, because they make it difficult for your smartphone, for example, to get the correct signal from the GPS satellites up in space. And yeah, underground it doesn't work at all. So there are also applications where you're not just placing sensors to sense something, but also to send out information. So, hey, I'm sensor A2, and I'm sitting at this location here. If you can hear me, you're somehow close by. And if you can also hear sensor A3, you're somewhere standing between us. So that gives you an idea where you might be in an underground mine or in a high-rise building or parking lot or whatever. So something where GPS-like systems do not work reliable or are not precise enough. Also, Internet of Things application. You can then extend this a little bit from just, okay, where am I in a city and where can I go in a city, to, of course, even more smartness for parts of cities or even whole cities. There are now more and more so-called smart cities that have a varying degree of smartness. So Songdo and Santander were among the first cities that claim to be smart cities, and they run different campaigns to install huge amount of sensors in their municipalities. So something like 12,500 sensors that they placed around the downtown districts of Santander's, where they then started to collect, for example, noise data, light data. They also integrated garbage disposal systems. So is this public garbage bin full, or can it be emptied next week instead of today? So those smart cities were sometimes planned relatively smart. Sometimes they just placed thousands of sensors without any real idea why they did it. Just essentially for like, yeah, we first collect the data and then we see what we can do with it, which is usually not the recommended way to do it. But other ideas were quite well thought through. So they try to do some kind of crowd management on sidewalks, to essentially the same as that you would do when you wanted to avoid traffic jams. So you know this street is always full, you can try to divert the traffic away somewhere else. Very closely connected is this problem of available parking spaces. So if you know at every moment or every given moment in time how many parking lots are available in parking space A and parking space B, then you can start providing informations to interested users. Okay, there are 5 more slots in parking lot A and 15 more in parking lot B. So you maybe go to parking lot B because you have a better chance of still grabbing an empty lot at the point in time where you are there. But in order to make this recommendation, you first need to know how many are there. You can then also try to make it more smart by taking into account historical data. You know that there's always a peak in occupied parking spaces around, I don't know, 11:30 because everyone is going for lunch, and then around 2, people are done with lunch and some lunch shopping, and then there are more spaces. So you can then make it, for example, cheaper to park there to increase the utilization of that parking lot, and so on and so forth. But we'll get back to that later. Those cities use the data from those sensors and analyze them not on site, as we'll see in many scenarios. They rather collected everything, put it into one big cloud, and then try to make sense of those data and then coordinate what was supposed to be the best course of action. So this now, after going through almost half an hour of examples now, that should have given you quite a good idea about at least some fields of applications for the Internet of Things. There are many, 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 many more, and it would be a whole lecture in itself to just go through all the relevant examples. I hope we gave you good idea of some of those applications. Now, from those specific applications, we're now abstracting a little bit. I emphasized again and again and again, I'm trying to learn something about my environment from placing sensors somewhere which then help me to extract information about the environment. So I'm trying to get data points. A data point is, on this abstract level, could be just a number like 40, it could be 0 or 1, it could be a letter. It is just symbol. And it's quite easy to get a lot of data, but just having a lot of data is not really worth anything, because the better you understand that data, the better you can use it to make something out of this. So just having a sensor that tells you 40 doesn't really help you. So you need to have more understanding. You need to have meta information about this number 40 or 0 or 1. And one of those information that then help you there, which make this data information, is if you can answer questions like who, what, where, and when. The 0 is a parking lot sensor that indicates 0, parking lot is empty or parking space is empty, and a 1 indicates the parking space is full. Excellent. Now all of those zeros and 1 that you're getting from hundreds of thousands of sensors suddenly start to make more sense. If you know it's a parking lot sensor, it is located in this address, and 0 means full, occupied, and 1 means full and occupied, and 0 means empty. So that makes data information much more helpful. Next step would be to derive further knowledge from those information. So the higher you go up in this pyramid, the more valuable the information. You're essentially going up in the value chain. So the next step after information is knowledge, where you're answering questions like how. Next step would be understanding, where you can essentially then appreciation of the why, and then wisdom is essentially the highest level of quality, or it has value level that you can achieve. So I already started this example with the parking lot. So if you go down here, we just have zeros and ones. 0 is empty, 1 is full. Then we already talked briefly about the information part. So who's parking at this lot? Where is this parking lot? When is the peak hour? What kind of vehicle is parking there? So those make data information. Knowledge in answering this, how do I implement tired charging? How do I find overstayed vehicle? So might be nice that you know that one parking lot or parking space has been occupied for 7 weeks straight, but where exactly is it? what do I then do? Or if I have like some kind of charging system for battery electric vehicles, how do I most efficiently charge those cars? Understanding then the why part. Why is my parking utilization low? What can I do? It goes back to this example that I mentioned earlier. Maybe my parking lot is always full by the end of the day because I'm a parking lot near a cinema. That means people are coming there usually towards the end of the day and not at 10 a.m. in the morning or at 8 in the morning. So maybe I can increase the utilization of my parking lot by making it super cheap until the end of the evening, while making more money towards the end of the day because people need to get to the cinema by car for whatever reasons, and then they're willing to pay a higher price and they're already in the mood of spending money because they want to have a nice evening. Wisdom does not apply here because we're just talking about parking examples, but we'll get back to wisdom examples throughout this lecture. But I hope that this gives you a little bit of an intuition and understanding on the more abstract level that pertains to all the examples that we discussed earlier. So first you gather data by extending this data with further information, with further understanding, you get to information, and then you synthesize yourself up this value chain. And it's pretty much the same in all of those examples. And I know the parking lot example is now one of those examples where you're like, is this really relevant for sustainability or not? Yeah, I know, but it's a really convenient example to explain this in very simple terms. Good. And this then brings us back to this figure that you have seen before, this data-driven smart circular economy framework that looks very, very similar to what you have just seen before. So you just have one additional layer downstairs. And I think they removed the understanding layer here, but it amounts to the same. You have connected resources, so the Internet of Things providing you data, which you need to make sense of. You give it context, so you know, okay, it's a parking lot, you give it meaning, and then you synthesize the wisdom, and you move up this value chain. Up to the end of the information part, we're talking about a so-called descriptive analysis. So what happened to the resource, or what does the resource describe in terms of happening? Diagnostic analysis is then why, how did X happen to the resource, or is noticed by the resource? Discovery, what better use can be made of the resource given the current condition? Predictive, what better use can be made of the resource in the future? And then prescriptive, how can use of the resource be optimized dynamically? And please note that resource can then be an empty parking lot or occupied parking lot, but it can also be maximizing the utilization of your smartphone, maximizing the utilization of your power drill, or really of, if you go back to this performance economy idea, actually the utilization of single atoms and molecules. So it doesn't really matter what this resource is and how you're monitoring or learning about this resource, this all essentially remains the same. And that being a little bit a mix of examples for the Internet of Things, abstracting from those examples, and then also serving as the motivation, okay, why could this Internet of Things be helpful to make the circular economy happen, or at least provide a building block for the circular economy? Now let's get back to the actual Internet of Things. We had now a short history, a little bit of introduction. Now let's look at some proper definitions. Similar to the circular economy, there's not just one definition. There are hundreds of definitions, and some focus more on this particular aspect, while others on yet another. So we'll once again look at a few definitions to give you an idea, okay, what are core components, what are core aspects of the Internet of Things, and then we're just going to leave it at this. You don't have to learn them by heart. We just want to make sure that you have a good understanding of what this Internet of Things is and that you can explain it in your own words. So the Cambridge Dictionary, for example, defines the Internet of Things as objects with computing devices in them that are able to connect to each other and exchange data using the internet. So I have a thing, it can compute, it can also talk in some language via some kind of communication means to another thing, and that is the Internet of Things. Wikipedia defines it as the Internet of Things is the internetworking of physical devices, vehicles, also referred to as connected devices and smart devices, buildings and other items embedded with electronics, software, sensors, actuators, and network connectivity, which enables these objects to collect and exchange data. So once again, the real world thing, it has some compute and talking power, connects with others to then exchange information. Technopedia defines the IoT as a computing concept that describes the idea of everyday physical objects being connected to the internet and being able to identify themselves to other devices. The term is closely identified with radio frequency identification, or in short RFID, as the method of communication. It also may include other sensor technologies, wireless technologies, or QR codes. So this is a little bit of an older definition of the early days of the Internet of Things, because back then, something like, if you're thinking back, like read this in the history slide, like 1982 for the beverage dispenser, 1991 for this vision for ubiquitous computing, and then 1999 for this Internet of Things idea by Kevin Ashton. In those days, you did not have, like in 1982, you did not even think about broad and widespread Wi-Fi coverage. There was nothing like wireless cell phone reception. People had phones at home with a cord attached to it. And back then, the hottest shit was something like having an RFID tag. So it's small, it looks like it's like, for those of you born after 2000, just imagine QR codes that did not have information in the QR code itself, but there was some kind of a chip behind it that if you swiped over it, or if you like put your phone or whatever, not your phone, some kind of a reader above it, it essentially makes like it exchanges information. So it's a similar thing like access tokens to buildings, or your university cards that you can put on over a payment terminal, just more dumb. This is what RFID sensors were, and NFC is essentially like this idea that you have for wireless payments with your phone. So, but in a very, very primitive way. And yet another one, I think is also our final definition example that we gave you. The IoT is the internet working of physical devices. I think we had this one. Yeah, that might be a note for Anand, because I think, yeah, the Internet of Things agenda from Tech Target and the other one, they are somehow overlapping. But I guess that's not really a big problem. So we'll fix that slide. You will get the fixed version later. Good. Anyway, back to the point. So what most of those definitions have in common is we're having a real world physical object that wasn't always designed with this idea of being connected to the Internet of Things being designed. So my coffee mug was not designed as a real world object to be connected with the Internet of Things. However, by adding a certain level of computing and networking capabilities to this real world object, I can make it part of the Internet of Things. Other devices have been designed with a way of only properly working as part of the Internet of Things. Without it, they would be useless. And this is now what we're going to use, at least for the next 3 weeks, to slowly but surely make our way through the different building blocks of the Internet of Things. So we'll start today with, on the left side here, we'll look at what are sensors, smaller computing devices, and actuators. And then in the next week, we're going to look at the connection between those devices, because it's not just the internet as a broad term or Wi-Fi. There are also, depending on your use case, other means of communication that can be helpful. Once I'm then done with collecting data, communicating them somewhere, putting them somewhere in the cloud, then I need to know, okay, what is this cloud? What are the different parts of those so-called IoT cloud platforms? And then the interesting part comes later. We're going to look at some use cases for applications where you will do some hands-on coding, at least for the non-mining students. And we'll also have a look at this analytic part, because all of the stuff here in the beginning does not make any sense if you do not do the analytics on the collected data, make them to information, synthesize wisdom, and so on and so forth. So this is like one of the core parts here, and usually happening partially inside of those IoT platforms. So let's start with sensors. As the name suggests, sensors help to sense. And we'll start with the very simple and stupid sensors, the so-called conventional sensors. They usually provide you some kind of status value. So they deliver, for example, a defined voltage value once the measured event has occurred, and then you can translate it into something. So, for example, if you have a so-called push button, if you push it, there is a circuit being closed, for example, some electricity flows for a second, and then you know, okay, the button has been pushed. There are also read sensors or hold sensors or light barriers that you might know from commuting by bus. If something is blocking the laser or this light sensor, the door might not close. It can also be a light sensor, for example, when the sun goes up, the doors for your chickens open so you can get light there. You can also have temperature, ultrasound, and radar sensors, which all work on a physical level. So they give you status values. Now, at this very moment, the light barrier is, there's something in between. Right now, someone has pushed this button or is pushing this button. Right now, the temperature is 20 degrees Celsius. So you get status values for right now. When you're pulling information from the sensor the next time, the status value might have changed. But you always have to go ask or talk to the sensor or make the sensor report back to you in intervals. On the other hand, we have the so-called continuous values. They provide a continuous value depending on the measured value. So this could be this is something that requires like an analog digital converter. So it could be the flow of water through a pipe where you have some kind of continuous, or when you're measuring electricity voltages. So either you have the status part or you have continuous values as part of those conventional sensors. But this is not the only thing where you have to essentially differentiate between sensors. It's not just status and then conventional. Even inside a specific type of sensor, and we have chosen the temperature sensors here as an example, there is still quite a big range of temperature sensors that are good for different purposes. We have listed here 5 examples for those temperature sensors. So the NTC thermistors, thermocouple sensors, platinum sensors, thermopiles, and digital sensors. And we listed some of the properties or defining properties here. So depending on your use case and what you need the temperature sensor for, you might or you have to choose what you essentially buy. And on one hand, of course, money could be one criteria, you just buy the cheapest, but does the cheapest also then satisfy your needs? So temperature sensors, as one example, where you can like really nicely differentiate between them for different use cases, is the actual temperature range that they can measure. When you are thinking about a temperature sensor in an agricultural context, or to control the temperature in your house, to decide, okay, this is when the windows should open or when the AC should be shut off or turned on. you're usually thinking about temperatures between, let's say, I don't know, minus 30 degrees and plus 40 degrees. Because below minus 30, depending on where you live on this planet, quite rare, and also an indicator that something is broken. Because if you're living in Clausthal and your thermostat inside your living room shows minus 40, it is more likely that the sensor is broken than it is actually minus 40 in Clausthal-Zellerfeld in your living room. But I'm getting a little bit sidetracked here. So you want to have a normal temperature sensor for agriculture or for smart home control. Let's say minus 30 to plus 40 or plus 50 is totally fine. However, if you're thinking about alternative applications, so monitoring a heater system that burns oil or something like that, you need higher temperatures. If you're going into the industrial part of the Internet of Things, let's say producing certain materials, you might also even need higher. So melting steel and something like that, you need higher temperatures. So you need something that can, on one hand, resist the temperature of the external environment. So this would be this ruggedness factor here. But also give you accurate readings for the temperature ranges that you are interested in. So this minus 270 to 1800 degrees Celsius thermocouple sensor is probably extremely overkill for your agricultural aspects, but you need it for soldering irons, exhaust gas detections, and so on and so forth. So this would be the one for those applications. However, quite expensive. Then you also might have scenarios where an accuracy of plus minus 2, 3, 4 degrees is totally fine. But if you think about the application for human health, if the temperature that you're measuring for a human is accurate to plus minus 5 degrees, that is a decision or is a range of life or death. If you're 5 degrees hotter, you might be somewhere at 42, 43 degrees core temperature, you are dead. If you are suddenly at 32 degrees Celsius, you might be going into, or you might suffering from like really really severe cold exposure. So there you need a much more refined measuring capability. While for the cryogenics and the soldering irons, plus minus 5 might be okay. I'm not an expert on that, but you get the idea. So that's why the temperature sensor is not just a temperature sensor. It is specifically tailored to a certain use case. And the same is true, obviously, for other kinds of sensors. It might not be the range that is then the most critical example there. It might be the size, and so on and so forth. We'll get to more examples, but this is like a super, super important aspect of the Internet of Things when talking about sensors. Do I get a status value? Do I get a constant, what was it called? Continuous value? And also what sensors do I specifically select for what use case? Then there are also, besides those conventional sensors, so-called smart sensors. They are complex sensors with integrated information processing. So while the traditional sensors that we had before just give you like a pure value based on physics and electrics, here you have some kind of processing already built into the systems. So that could be programmable temperature sensors and thermostats. It could be a magnetometer, so the smart compass, but electric compass. It could be so-called MEMS, micro electromechanical system sensors, like accelerometers or gyroscopes. You most likely know them from your smartphones. Again, so if I hold my phone like this, looking at the screen and calling someone, the light of the screen is on. If I put them on my ear, there's a sensor that notices the distance. Okay, so I can turn off the screen. But the gyroscope and accelerometer is also helpful for not just for detecting motions in general, but also for navigating. Which direction am I turning has an impact on the for example, the navigation system that tells me where to go next. Or if you're using it to track your running activities or your step counters, like all this is essentially acceleration and potentially the gyroscope for an angular to get an angle that is produced there, those so-called smart sensors. So they have integrated information processing on top of what we discussed with the previous sensors. And the list of those sensors goes on and on and on and on. We'll by no means have time to look into all types of different sensors. So we just have some examples here. So I already talked about the distance sensor here on my phone that decides should it turn off the screen or not. You also have a distance sensor in most modern cars. When it comes to parking, it starts peeping the closer you get to an obstacle. You might have ultrasound or radar or infrared with position sensitive detectors. We, for example, have some in our greenhouse where we have a water barrel, and the ultrasound sensor essentially measures the distance between the lid and the water. The more rainwater we have in the tank, the closer the traveling distance between the ultrasound sensor and the lid to the surface of the water. Yeah, there are many, many more. Cameras with built-in image processing are a complete story in itself in terms of capabilities and what you can already do on the camera and what is limited by the camera's computing power. We'll have a few examples in the next few slides. So yeah, we talked about or briefly mentioned those peer sensors here in a second. Peer sensors are most famously known for essentially triggering light bulbs when you walk close by. So instead of having the light in your garden on 24/7 or at least the whole night, essentially you have this motion sensor that detects when you're walking by, turns on the light for 5 minutes, and then waits for the next thing to activate it. So humans and animals emit heat energy visible on this infrared spectrum of these peer sensors, and the peer sensor detects changes in infrared radiation, hence detecting when something living is walking by, and then you can trigger an action accordingly. LiDAR is one of those technologies that became more and more popular, especially in this context of self-driving cars or autonomous cars. Tesla most famously is refusing to use LiDAR, and they are convinced that they only need cameras and LiDAR is not necessary. Other companies like Waymo in this space, they are either preferring LiDAR or using a mix of LiDAR and cameras. So LiDAR stands for light detection and ranging. So you have something usually on top of the car that sends waves of light or of something in every direction. And depending on how it's reflected, you get or you are able to reconstruct an image of your environment. Simple reasons you can imagine it a little bit like what bats are doing. They're sending out those ultrasounds, and depending on how it pings back, they can orient themselves. Not quite accurate, this comparison, but it's close enough for the sake of just making this one slide example. Camera image processing being for us nowadays mostly used in this context of object detection. So either in the security and surveillance aspect of detecting is a certain person there or tracking a certain person. So thinking about all those spy movies that you have watched, or for self-driving autonomous cars that have to decide, is this what's in front of me that I detected? Is it a human being, or is it just a flying trash bag, or is it just fog, or similar means? Here, this example pretty nicely demonstrates this in like super simple terms. You have a picture, you separate it into different squares to be analyzed. you put this into a machine learning or AI system, and then based on its previous training, it decides, okay, this most likely looks like a dog. The dog is sitting in front of a bicycle, and we also found a car there, but we did not detect that there's also a partial tree available, maybe because the system wasn't trained to detect trees. One of the most common IoT systems that you're carrying around with you most of your day are smartphones, and those smartphones also already have quite good or are well equipped with already existing sensors. So we talked about the accelerometer and gyroscope before. We also have a gravity sensor. We can use rotation sensor. We have some kind of a magnetic field, proximity, GPS, orientation, so that you can decide, am I watching a movie like this or this on my phone? You have a light sensor, you often have a thermometer, you have a barometer, you have a humidity sensor. Like my phone always complains when there's some kind of dirt or humidity in the charging port of my phone, and then rejects the charging process until it's perfectly dry again. So there's like a lot of different sensors already built in your smartphone that you don't really think about on a daily basis. What might be interesting to consider here is that some of those sensors are actually hardware based. So there's a special purpose hardware built into your smartphone to do those measurements or to sense those information. Others are purely software based. So that means you are essentially calculating based on an algorithm the information or the status value of that sensor without having a real hardware based measurement. It can be the case that those input information are implicitly derived from a different sensor, and then you do some magic calculations, and then you understand, okay, there was a 30-degree rotation here, or this is the orientation of the smartphone. But there's not an explicit sensor in there that measures the smartphone orientation to change the screen in this example. So we looked at different ways to sense your surrounding, to learn something about the environment that you're in via different sensors. So stupid conventional sensors to more smarter sensors to camera sensor systems, which actually have such a high computing power built in that they can do object recognition on the fly without much delay. So quite a big range of different sensors. Another important aspect between sensing the environment is also to interact with the environment. And this is where the actuators come into place. Actuators can be a lot of things. It can be something simple as an LED that starts blinking on a screen. It can also be a light bulb that goes on. Those are things how you interact with the environment. And the light sources here could be used as indicators for certain events. You could also have acoustic indicators, so a bell, a buzzer, a piezo sound transducer. You can have electric switches and drives, but you can have also motors. So if temperature goes above a certain value, start the AC. If CO or CO2 levels go above a certain value, automatically open the window in Benjamin's office to get some fresh air in so that he stops talking so much nonsense, something like that. So those are potentially being triggered based on information that you gathered about your environment to then interact with the environment. We'll keep this quite short because we'll think a lot about this. Okay, what do I now do with the information from the sensors that are synthesized to then do certain actions? And those can be so manifold that it doesn't really make too much sense to look at this actuator action because it's very, very specific to the use case. So we'll get back to this based on use cases. What is another important aspect or a more important aspect on this level that we're currently looking at is the source of power. If I want to continuously monitor my environment and interact with my environment, I need energy, either to run the sensors and to then communicate the data that I've collected, but also to interact with the environment. You need some kind of source of power. And in your smart home or at home, this might be a no-brainer. You just connect it maybe to your normal grid, and then you're fine. However, if you're thinking about more broader applications, you might not have the luxury of a normal wire connection. So if you're placing sensors on a farming field, you might not have wired electricity connections. So you might have to work with batteries. You might also be able to use something like solar energy to every now and then recharge those batteries. But there are also other sources that you can use to run your sensors or actuators. So there are piezo generators. They convert mechanical energy like vibration, motion, and sound into energy. You have the so-called RFID checks, so radio wave energy generation. When you put an energy source over those tags, they emit certain information. You can use thermal energy, of course, also radioactive power sources. So there are different types of power sources that you can tap into. And they're mostly dictated by how much energy you need and where does your sensor or your actuator live in its field of application. So in a smart home, you go for wired connections. Somewhere in the field, it's probably something battery or solar power based. If you're talking about water sensors, you might not go for the solar option anymore. You have to go for something else. You get the idea. So on one hand, it's dependent on your location and where you use it. The second part is also how much energy do you actually need? Because the energy consumption depends on different factors. And this is not a complete list. This is just something to, once again, give you an intuition for that. So one of the most relevant parts here is the computing power. If I want to do something like object detection on a live stream of camera images, I need a lot of computing power. I not only required to constantly have the camera up and running and to record images or streams of images, I also then need some kind of an AI or machine learning model to run on top of this and then do the object detection on the fly and give you feedback. So that's quite powerful already. Active sensors, so what sensors are running on my system, is just the temperature sensor that gathers the temperature once an hour or once a day? Or is it, as I said, this video stream from a camera? How often do I collect this data? Pretty much related to what I just said, number of sensors, but then also how often do they pull sensor information? How do I communicate the data that I collected? Can I also just put them through a wire and back to some kind of a central main server? Or if I'm once again on a field or in the forest, how do I get that information away? Depending on the method of choice or the communication approach of choice, I have different energy constraints and also energy requirements. How often do I communicate those information? Once every millisecond, once a minute, once a day, once a year? And are there other energy losses? So is it super cold? Is it super hot? Is there an inefficiency of the energy supply? Do I need to run certain actuators, LEDs, and displays as well? So those are just like some example of things that will cost you power and that you have to somehow get from somewhere. And here's a small example for a Bluetooth sensor tag kit, the so-called TI sensor tag C2650. And we went through the trouble of getting those information from the technical specification. So in standby, this sensor uses 0.24 milliamp. Just standby, just being on. If it's switched on, but all sensors are off, we're talking about 0.33 milliamp. If all sensors are switched on and we're taking a measurement every 100 milliseconds, so 100 milliseconds per sample, and the data transmission is via Bluetooth low energy, we are already going up from 0.33 to 5.5. So quite a heavy increase. And if it's just the temperature sensor so the isolated temperature sensor takes 0.84, the light sensor 0.56, accelerometer and gyroscope 468. So they are among like the most heavy users, and the barometer 0.5 MA. So if this is now connected to a wired connection, you just have to worry about your energy bill. That's totally fine. That's not a big deal. But if you have to run it with the battery, you need a battery that first can live in that environment where you're placing that sensor, but then also you have to somehow connect it. It has to fit in that device and so on and so forth. So this TI SensorTech C2650 is usually run with a CR2032 battery, which has 240 milliamps. So the maximum that we can get out of this when it's like running with sensors is a runtime of 44 hours. It means in less than every 2 days, the battery is exhausted and I need to swap it. That might be fine for some use cases, but not really for all of them. So that puts you in this position where you have to think about, okay, how can I make one? Like either you get a bigger battery or you have to reduce the battery consumption of your sensor system. So does it always have to stay on with data transmission and everything and sample at 100 milliseconds? Is this really necessary at all times? If yes, okay, then you have to deal with it. But is it maybe enough to get temperature measurements once an hour? Do I really need a gyroscope or not? Or maybe temperature, light, and barometer is fine because it's a weather station in a farm field, and I don't need accelerometer and gyroscope at all. Can I measure those values every 100 milliseconds, every second, every minute, every hour, once a day? And can it stay in standby for the rest of the time? So this gives you an idea on how to extend the runtime as much as possible while still getting the information that you need. And once you have optimized that, you can, of course, you still have this like idea, okay, I cannot do it wired, but I have to do battery. I can try to get the largest battery, but it has to fit into the system. Can a battery provide sufficient voltage and current? Because not every battery provides you the same current and voltage. You might need a certain minimum to operate your system. Can the battery be replaced if necessary? So I have to replace it every 48 hours and it cannot be replaced. That essentially means I have to bring a new sensor kit every 48 hours, which is also not really sustainable, but also quite expensive. What's the weight of the battery? So think about a drone. I might have a really cool 50 kilogram battery that can power my drone for 2 weeks straight. But if my drone can't lift off with that 50 kilogram battery, it's no good. How often do I have to charge the battery? How long does it take to the battery to be charged? Is the battery exposed to some kind of environmental challenges? So it could be temperature, could be rain, could be, I don't know, falling rocks or whatever, or animals trying to play with it. Is deep discharge a problem? And then also the different types of battery give you also different constraints that you need to account for. So last but not least, we'll make a very short dive into different IoT devices. So most of you have something like a smartphone, a tablet, a computer, a notebook, and you can of course connect your sensors to those. but you probably would not use them to deploy larger sensor networks on a large scale. So you rather prefer something like a smartwatch or something even smaller. On one hand, due to its size and weight constraints, but also a 2,000 euro notebook for every temperature sensor that you want to place in your home might be a little bit overkill. So you're looking for just enough computation power for the smallest budget you can get, and also for like some, of course, other factors like generalizability and so on and so forth. But my main point being, you don't need fully grown computers or smartphones to run those sensors. And this is why those IoT devices like Arduinos, Node MCUs, or Raspberry Pis are very popular in this field. On one hand, you can use them in real industrial applications, but they're also super good for prototyping purposes as part of your study program, but also in research. So we have, tons of them, and we're using them on a very regular basis. So Arduinos are those small boards on the left. The Node MCUs are there as well. The Raspberry Pi is probably the most well-known mini computer. So the Node MCU and the Arduino, they are really like dumb compared to the Raspberry Pi, while those Raspberry Pis are actually pretty working mini computers in the size of roughly a credit card. In terms of its dimensions, a little bit higher, but it has a CPU, it has a GPU, it has connectors for internet, for USB. You can connect it to a monitor and can use it as a normal low-powered computer, but it also has pins and connectors up here, like the Node MCUs and the Arduinos, to connect different types of sensors there. Usually those IoT devices also have a certain way of communicating themselves. So built-in Bluetooth, Zigbee or whatever, or just normal Wi-Fi, or some other kinds of more exotic protocols. We'll get into that in our next lecture, which they then usually use to either transmit the information, the data that they are sensing to some kind of a central service, or at least communicating them among each others, thereby forming so-called wireless sensor networks, WSN. Those are usually then low-powered devices like this Iris or TeleUSBs or the Arduinos that you just saw. They have standardized connectors for sensor boards that you can put on them, and they also use low-powered communication protocols. So usually in those wireless sensor networks, everything is low powered, which means very, very limited in their capabilities, but often fine enough for quite a lot of those large scale sensor applications that you might want to have. Those IoT devices, whether they are now really built based on those Raspberry Pis or Arduinos or like some other kind of embedded chips, can also be consumer products that already have some computing power and smartness built in. So we already discussed the surveillance cameras multiple times throughout this lecture now. So there is some kind of computing power in there, and also means of communication. Smart locks, smart lights, smart watering plant systems. They are also part of those IoT devices because they already have this built-in computing power. In the industrial space, we're looking at pretty much the same, just for industrial applications and on a larger scale and more serious. But we'll get into those when we're discussing different examples, but also the subsequent building blocks. As one of the final slides, I'm not 100% sure if there's yet another behind that. I would like to make a quick detour to putting or placing those IoT devices, sensors, actuators, power sources, and everything related into the environment. If depending on where you're using it, you have to protect it against the environment, depending on the use case. So in the smart home, most devices are mostly just protected in such a way that no one can easily get to the electric part, so that no one might get injured. So if you have, I don't know, a smart light bulb, yeah, it's essentially the only thing that is relevant is that no one can get hurt when they are touching the light bulb, that they don't get electric shock or something like that. But if you have an outdoor light bulb, it has to deal with wind, with rain, and with other exposure to harsh elements. And this is where the so-called IP codes come into place. So they're ingress protection codes. So they are giving information about Jesus, I'm running out of coffee. They give you information on the degree of protection provided by mechanical casings and electrical enclosures against intrusion, dust, accidental contact, and water. And it's a 2-digit system. The first digit details the protection from dust. So 0 means absolutely not protected, no protection from dust. 6 on the other end of this metric means it's dust tight. There is no way that dust can get in there. Might be quite relevant, for example, in mining operations. Depending on what you're doing there, there is quite a lot of dust that could come into your sensor systems or other electrical devices and so on and so forth. The second digit, also ranging or starting from 0 on the range going up to 8, gives you the protection from moisture. So 0, once again, means absolutely not protected. It's not allowed to get close to anything watery, while 8 means I can protect it against, it is protected against submerging. I can throw it in the water, I can go diving with it. So for example, the smart watch here, I'm not sure if it's what its dust protection level is, but it's certified for diving, I think up to 30 or 40 meters, something like that. Way beyond my use case, but you can submerge it, nothing bad is going to happen to it. And then for both of those metrics, there are some numbers in between. So let's say you have an IP68 smartphone. It means it's completely dust tight and it's protected against submersion for a longer time. So you can go diving with it and also throw it in the sand or put it in a super dusty environment, and it's going to work fine. An IP08 device cannot handle dust, but is fully protected against submersion, for example, in any combination in between. So might be your actual devices themselves, but might also apply, for example, to auxiliary hardware like displays, for example. And that leads us to the end of this lecture. So we had a short recap before we moved into a brief overview on the history of the Internet of Things. We looked at a lot of examples and applications for the Internet of Things. We looked at the definitions of the Internet of Things. We looked at sensors, we looked at actuators, and we looked at some IoT devices, admittedly very briefly, but that should give you some idea of this lowest building block of the Internet of Things before we go on to the means of communication in our next lecture. I will give Anand the pleasure to now give a quick overview on exercise 5. And then we're going to cut the recording and meeting in for the Q&A session. But first, Anand, please.
Can you hear me?
Yes, we can.
Okay, so exercise 3 is going to be, exercise 5 is going to be the first programming exercise for computer science students. So basically, the whole exercise is going to be geared around taking in data from different sources, in this case, weather data. And because data from different sources tends to be packaged differently, some can be in JSON, some can be in other file formats. We are going to be parsing raw data coming from other sources and then putting them all together inside of one aggregated um, data format that is available to use for whatever application you have. In this case, the application is being a smart charging station. Obviously, charging a station with a solar panel is complicated because it depends heavily on the weather, particularly whether it's sunny or not, obviously the time of day, and also whether or not it's super cloudy or raining all the time. So a lot of things really affect how much electricity you can produce. And this exercise is about figuring out how much or what type of weather you have. The next exercise from next week would be the perspective of, okay, once you know what the weather is, can you please figure out, okay, how much electricity can we produce? Yes, so you will find on CoCalc already assigned to each of you the exercise. So it'll just be a folder called EO5. Please read the exercise sheet on GitHub, and also the various instructions inside of the Jupyter notebook itself. Instructions were more detailed there, but essentially it's just one file, same as before, that you always have to keep changing.
Good. Thank you very much. That was today's lecture. We'll cut the recording now and meet again at 4 p.m. So in 12 minutes, according to my clock. That gives everyone time to refill their coffee mugs or use alternative preferred beverages. So thank you very much. You can already put questions in the chat. We'll then answer them one by one during the Q&A session. Thank you very much and see you all again next week. Bye-bye.